Hello everyone, and welcome to Understanding Physics, in which I will try to guide you through understanding physics. So, in General Physics 1, we want to talk about energy, work, and power, which are some quantities in physics that we always use. So, first, we want to discuss what is energy. So, the way that I define energy is that it is a source that encourages change. For example, if you have a object to be at a higher ground compared to the object at a lower ground, this object wants to change its energy so that it will later be at a much more lower state. And same thing with kinetic energy. If something has kinetic energy, it will want to try to move. So basically that's the way that I define energy. And and energy is a scalar object in which that there is no direction in energy. So, so there's one of the most fundamental laws in physics, which is the conservation of energy. This basically this basically states that energy can only be converted. So energy can only be converted from one to another. So let's say if you have kinetic energy and then you want to change it into potential energy. You can only change the energy. You cannot create a new energy or destroy the same energy. And so this analysis is one of the most important parts in physics for you to always remember. So to discuss about energy, work, and power, I want to introduce this this object which we will call as a system. So so we might have already talked about system multiple different times, but we didn't truly define what is a system. So I want to define a system is a area with a imaginary boundary. So what does this actually mean? So basically, if I have to state, basically this block is a system. This means that this means that the block has a boundary, and and all of your this is where you do all of your analysis, and every law of physics must be upheld within this one block of system. So this is one of the most important things for you to always remember, is that you need to define a system in order for you to solve a physics problem. So we have talked about energy, and so what are some forms of energy? The first thing that we always normally discuss is work. So basically work is defined to be Fx multiply that by delta x. So basically it is the amount of force that you need to move an object from one place to another. So basically, if you displace the object higher, therefore you will later use much more work. But but if you use a higher force for you to move the same length of object, you will also need higher work. So this is basically like the amount of energy that you waste in pushing a block. Let's say, for example, if you are trying to push a block from one place to another, and let's just state that you use lots of force. That means that you push much more harder. You will later feel much more tired once you have already moved the block to this other place. Compare that if you actually use a lower force. Let's just state that you push it slightly together with others, you will feel yourself not using much more energy. And so this is one of the key concepts for you to always remember about work. And so and so another thing about work is that this could actually be written as F vector, multiply that by delta R vector. And so what does it mean for something to be multiplied by another vector? Well, there are two different cases. The first is what we call as a scalar product. The other one is what we call as a vector product, or sometimes called as the cross product. So, for a scalar product, or a dot product, this basically means that you will try to multiply component by component. So let's just state that if you have a vector ax, a y, and a z, and then you dot that with another vector, bx, by, bz. Basically, the scalar product will tell you that ax, bx plus ay, by plus az, bz is the scalar product of these two vectors, a vector dot b vector. And basically this is equal to the length of A, multiply that by the length of B, cosine theta. And so this is one of the most interesting properties of a dot product. And so if you try to analyze this for our work, we could just see that basically if you have a certain force going in this direction, and then you are moving it in a delta r in this direction. So basically, if you are trying to find the work, that means that you are trying to find, let's just write this to be delta x. We can figure out that the vector going from here to here would be fx. And so we could state that fx dot delta r is basically the same thing as if you call f cosine theta delta r, or delta x. And this is basically the same thing as if you write f vector dot delta r vector. And so another property that you also need to remember is that a dot b is the same thing as b dot a. And also a dot b plus c is the same thing as a dot b plus a and c. And so this might seem obvious to you, but normally in mathematics, it is not always this obvious, in which you have an operation that has these two properties. And so you need to always remember about this. And so that is what we call as work. So basically in here, we have assumed that the force is constant among the delta x. But what if we are varying with our forces? So the way that we will actually figure this out is that we need to use calculus. So basically, you could write the small work to be the force during the certain point, multiply that by the dx. And so basically, you would figure out that the work will later be from x1 to x2 of the force dx. And then you could actually extend this into a 2 or 3 dimension. So this one is 1 dimension. So in a 2 or 3 dimensional system, you could state the work to be the integral from the first position to the second position of the f vector dot the r vector. And this is where vector calculus comes in. So if you don't know about vector calculus yet, I encourage you to actually learn a little bit about this so that you can solve much more advanced problems. But if you don't already know about it, it is okay if you continue with this journey because I won't really discuss uh, cases in two or three dimensions. So we have talked about work and its formula, and so now we want to try to discuss a little bit about some special cases. For example, if you are trying to stretch a spring from a point, let's say 0, towards a point x, the force that the force that you need doesn't truly matter. What what truly matters is that you are moving it from one point to another. So if we start from 0 towards x, and then let's say we are pulling this with the force the same as the force going backwards, or like, yeah, basically the restoring force. So we could write this as kx dx. And so eventually you will later be able to stretch it until this point. And this will later, if you evaluate this integral, you would be able to obtain kx squared over 2, which is the work needed to move the spring from its equilibrium point towards a certain point x. And here is one of the important things. There is something that we call as a conservative force as well as a non-conservative force. So basically a conservative force doesn't really depend on how you pull it. So basically, if you are pulling it with a much more force and then after that you slow down, it won't truly matter. Compare that if you try to pull, let's say, an object in a friction body. The force of friction is non-conservative. So basically, what this what this means is that if you take a different path for you to pull the object, you will get a different work, which is one of the most interesting facts in physics. So, depend on how you pull it. So, one of the interesting facts is that a spring is a conservative force. So, we have already discussed about that. So we would also try to discuss one of the other interesting situations, which is if you have an object falling from one place to another. And we want to figure out what is the work done by gravity. So, so in here, we will figure out that there's weight that is from 0 towards a certain distance h. Well, yeah, it is. Well, it is at the. It should be at the. Oh wait, no, never mind. It is. It is at the correct direction. So you want to move it from point 0 towards a certain point. Let's say h. So the work done by the weight will later be from 0 towards the h, which is technically the negative of h, and then the force, which is mg. Well, yeah, technically it is negative mg. Well, yeah, we'll just state that to be y positive. So yeah, this will be positive dy. And so if you try to solve this integral, you would later obtain it as mgh, which is the work done by gravity. And so this is another special condition for work. So we have discussed about special cases in work. So now I want to try to discuss about one of the important energies, which is kinetic energy. Kinetic energy is the energy which comes from velocity. So this will later relate a lot with velocity. And the way that we'll try to derive this is from work. So you know work to be the integral from the first point to the second point of f dx. And we can write f to be m dv over dt. dx. And then if we move the dt to the other position, we would be able to obtain this to be the mv dv over dt, or basically it is basically the no, wait, sorry, this is dv. Yep, there shouldn't be any dt's there. So what you get is that it is the mv dv from the first point to the second point, or basically it is the integral of the momentum with respect to velocity. And this is basically equal to half mv squared, mv2 squared minus half mv1 squared. And this is what we call as kinetic energy. So kinetic energy is half mv squared. And then the net work must to equal to the change in kinetic energy. So basically the way that you could actually think about this is that if you have a system, and let's say it has a certain kinetic energy, let's say K1 currently. And so now if you try to apply a certain work into this object, this will later become a system with K2, where K2 must to be the work plus K1. And this is one of the important things, is that this is the conservation of energy. So basically we figure that the work is the change of kinetic energy, which is one of the most important things for you to always to remember. And by the way, the units of work or energy is something that we call as joules. So joules is basically Newton meter, or basically if you write this in the very long way, it is the kilogram meter squared per second squared, which is a very long name for you to remember. So instead we use joules. But there are other units in which we normally use. Sometimes we use calories. Sometimes we also use erg for a centimeter gram second system. And lastly, you could also use the electron volt, which will later deal with a very small amount of energy. But for now, we want to focus a lot about joule. So, we have talked about kinetic energy. So, what is power? So basically, you could state something to have high power or low power. So basically, if you think about something that has high power, it is like basically high energy within a short amount of time, while low power is that you have a large amount of energy over a long time. So basically, it is like how fast you want something to be done. It is basically the same thing with distance and velocity. No, sorry, distance and speed. So power is the rate of energy, rate of work, and its units is watts, which is joules per second. So the same thing as in kinematics, you could write power to be the p bar is the delta w over the delta time. And so if you take the limit, this will later become the instantaneous power. So if you take delta t towards 0 of delta w over delta t, this is the same thing as dw over dt. So basically the derivative of work. And so you could actually write this from here. As long as the power is constant, you could state that the work will be the power multiply that by the change of time. And then for the general case, work is the integral of p dt. And then there's another important thing for you to remember, is that you could write power in terms of velocity. And the way that we'll actually discuss about this is from work. So work is force times force times the distance. And and let's just actually do this over a short time period. So F vector dot R vector over dt. And so basically the force won't change across time. We will just state that the force will change depending on the position. So basically we could write this as the F vector dot the dr vector over dt. And this is F vector dot v vector, which is basically what we call as the power. And so that is all of the topics that I will try to discuss today. And so now I want to discuss about how do you actually visualize the the conservation of energy. And so and so the thing that I will discuss is from a case in which if you have a spring, attach that to a mass, which I simulate in the following simulation. So here is my simulation for a spring, for a mass attached to a spring. So you can see here that I have this red object as well as the force vector, which is the black vector here. And this basically symbolizes what is the spring doing on this point mass. And so after you do some computations in the physics, you would later be able to find this guy to move oscillating, which we will later discuss in chapter 11, I believe. And so if you see at the top here, this this left one discusses about the potential energy, while the right hand side is the kinetic energy. So basically what the potential energy here discusses is it is basically the work from the spring. So let's just state it is the work by the spring, while the right hand side is the kinetic energy of this object. And so this middle one is the amount of energy used. As long as we add this first one and the second one, you could see that the colors are changing. So from purple it goes to blue, and then from blue it goes to purple. You could see that the purple goes to 0 when it is at its maximum point, and it will be maximum at 0. And so if you try to increase the stiffness of the spring, you would see that the energy is much more higher. And then if you change the mass, it won't really change the energy, which you could actually compute from the kx squared over 2. And so you could also discuss about the maximum position. Let's state if you put it at a much more higher position, let's say at 2, you could see that it requires much more energy for you to do so. And so that's the simulation, and I hope this will try to bring your understanding much more further in physics. So thank you very much, and I will see you on the next video.